Okay, it's 4 o'clock, so let's go ahead and get started. Good afternoon, everyone. How's everyone doing today?
Doing well.
Good, good. Tired? Yeah, it's tiring. I've been talking, with a lot of you guys, throughout this semester, and I know it's hard. We've been at this whole pandemic thing for over a year now, and then I can see that it's really taking a toll because it's one thing that maybe it's more convenient because you're driving less or something like that, and for an entire year now, like you've basically been taking classes from your computer, and so your home, your school, your work, everything's taking place in front of a computer, and that gets really exhausting. And because, like, I know for me, I'm usually a big guy on physical separation of like work and home, and so I like to do my work at work, and I like to do my home stuff at home stuff, whatever you do at home. And when you start to blend those two, it really kind of feels like you never really escape from it at all. And so, now that we've been kind of keeping this up for a year, I can I you know I can I can feel it that it's tiring. It's tiring for me too. Yeah. It's we're doing a different type of fatigue. So I know you guys are fatigued, but this is we're talking about material fatigue for this one. Yeah. Okay. So with that said, I do want to remind you guys that we do have a midterm upcoming this week. And so Thursday's class will be a midterm session. And so this will be the only time that I'll be lecturing this week. And then Thursday we'll take our midterm. And so on Friday, I recorded the review session. I think that the two things that people wanted to see most were weak forms and finite element forms. And so I did my best to review those and do an example problem for each of those. Okay. And those are definitely good to know for the exam, both of those. And so I would definitely study that review session pretty closely. Okay? And then we'll take our exam on Thursday. Right? And so besides the exam, the only thing I really have left in terms of content for this class is really just a bunch of Ansys stuff. And so today, we have a little bit left to finish up on the lecture notes on verification and validation. And so we'll finish that first. And then from there, we'll launch into what I call basically Ansys demonstrations or Ansys tutorials. And so these are activities that are based around, some important features I think are good to know for Ansys, but I think are not like part of the core. It's not a core Ansys skill that you would normally see for the activities. And so, I have quite a few of these demonstrations planned. And you'll see two. I'll see if I can squeeze in two today. And so for these demonstrations, you don't have to turn in anything, and so you're of course free to follow along if you're interested, or if you want to watch the video later and follow along, that's fine too. But there's nothing to submit. And so for these activities, because or for these demonstrations, because these topics are a little bit more niche, and so I'm sure some of you will find these topics really interesting, either for your final project or or whatever else you want to do with finite elements. But I know it's not applying to everyone, and that's kind of the difficulty with such a big software like Ansys, because there's so many different features. It's hard to find the topics that really apply to everyone. And so I want to make sure that I cover some of these topics because they're really important, but they're not going to apply to everyone. That's why I have them more as like optional kind of demonstrations that which I think are really cool to learn, but may not be applicable to you or your final project. And so today we're going to learn about how to do anisotropic materials in Ansys, which I think is a big one for those of you who are working with. I know several of you are working with 3D printed parts, and so that this will be useful for that. Or if you're working with some kind of wood or something like that, where the material is not isotropic. And then we'll perform fatigue life analysis in Ansys as well. And so what that is that's the Ansys analysis type where you can compute things like factor of safety. You can compute or estimate how many loading cycles a part can have before it fails, things like that. Okay. Okay. So any question? Are there any questions I can answer before we get started for today? Okay. All right. So let's go ahead and finish up. So we had one more page that I wanted to do in the lecture notes for verification and validation. Okay. And specifically, we're talking about validation. And so just to kind of jog your memory, because I think it's been a week since we've seen this, Validation is this idea that, that what you run in a finite element simulation is really just an approximation. Okay. Because it's something that's basically done totally on a computer, and so it's not actually something that's actually happened yet. Okay? And so in order for them to be useful, these approximations have to be as accurate as possible. Okay. And what I mean by accurate is, they should closely replicate what's happening in reality, right? It may not be exactly the same as what's happening in reality, but it should be close enough that you can draw, some engineering conclusions for these, right? Because an approximation or prediction is no good unless it actually happens, right? And so, one way that we can increase our faith or increase our accuracy in these approximations is to perform validation, right? Excuse me. And so validation is basically are essentially methods that you can use to assess whether your finite element simulation is a good representation of reality. Okay. And so the way this is typically done, kind of what we talked about a week ago, was that normally you would perform something called a validation experiment. I say we, but really the people that typically do this are the people that work for Ansys or the people that develop the software. Because essentially what you do with the validation experiment is that you take a finite element situation, and so you mesh your geometry, you apply your boundary conditions, and you see the results, and then you replicate that exact same situation within a laboratory, right? And so I think the example that we gave last time was a cantilever beam, right? And so you would set up two cantilever beams. Okay. And you would load them the same way, except one of these would be in the lab, and one of these would be in like Ansys or some finite element software. And then what you would do is you would compare the results, assuming that all the loading and all the boundary conditions are exactly the same, you should get the exact same results or very close to the same results in your finite element simulation as compared to the validation experiment, okay? And so, behind the scenes, this is what Ansys, the company, is doing to basically assess and to basically prove the accuracy of their software, okay? And that's kind of what you pay the big bucks for, and that's why Ansys costs so much money, right? Is because performing these types of experiments isn't cheap, and it's usually pretty expensive, especially for the wide range of physics that Ansys can do. And so we have to pay for those lab techs, we have to pay for those engineers that do this, and so that's where their money goes. Okay? And so most users, you're not going to run a validation experiment like this, because usually it's a pretty costly thing. And so for users to validate their simulation results, there's alternative methods that you can use. Okay, so any questions on this so far? This is just kind of a recap from last week. They're 3D printing houses now. Yeah, it's crazy. I've seen those things too. Really cool technology, but yeah, it's crazy how far everything's gone. Okay.
I have a quick question. Sure. Yeah, will we need to apply these concepts to our final project?
Yes. So and so you're not going to do an experiment for your final project because a lot of time, a lot of you guys are doing things like finding the stresses in the Leaning Tower of Pisa, and so I don't want you to recreate the Leaning Tower of Pisa in your house. That would be amazing in its own right, but not required for this project. And so there's other things that you can do, maybe not to validate your simulation results to an exact tolerance, but what I want you guys to do is I want you guys to perform some sanity checks. Just to make sure that the results that you're getting from your finite elements is reasonable and it makes sense. And we'll talk about how you do that later on in the lecture today. Okay. And so that's kind of the gold standard. And so if you're going to work for a finite element company, one that develops the software, you can expect to be doing a lot of these tests because they kind of form the backbone. And it's what people refer to when they say that our code is accurate. But what if you don't have the capabilities to run an experiment, which is, and most people kind of fall in this bin. Okay? And so one way that you can perform, it's technically not validation, but I call it like a sanity check. Because ultimately the goal with validation is just you want to make sure that what the results that you're getting from your finite elements isn't just bullshit, right? You want to make sure that it's actually something reliable and something that you can draw realistic conclusions from. Okay? And so if you think about how you do how you approach a lot of your other classes, right? And so say that you do like a problem in like heat transfer, or maybe a problem in structural mechanics, right? You run through the problem and you compute your results, and you say that the temperature here at this location is like 100 degrees C. Okay. And so as you're writing that down, one thing that you usually like to do is say, okay, does this make sense that my computations get me this 100 degrees Celsius here, right? And if your situation is something like you're computing the temperature of a snowball, right? And for some reason you're getting 100 degrees Celsius on that snowball, it's probably something went wrong along the way that you didn't get the right solution, right? And so those are the kind of mental sanity checks that you have that you should always be doing when you're doing these engineering calculations, because a lot of times what can happen is that you make kind of one small error, maybe you flipped a negative or something like that, and that causes your entire solution to go really bad. Okay, and so sanity checks are a key part of any kind of engineering analysis, and finite elements are no exception. Okay, and so kind of the way that I think of sanity checks are I kind of think of them as simple calculations. Right? Simple calculations or simple checks that the engineer performs to make sure that his answers make sense. Because a lot of times, if you made some kind of error within your setup, or you made some kind of error in your calculations, if you perform a sanity check, a lot of times you can catch those kind of right away. Okay. And so the way I want you to do this, for your final projects, and a good way to just do sanity checks for finite element simulations in general, is to check against what I call a simplified model. And so a simplified model is, and I know a lot of you have kind of written about this already in your proposals, but a simplified model is basically some kind of, analytical equation or some kind of maybe algebraic equation that you can solve by hand that kind of emulates your finite element model. Okay. And the idea is that, the simplified model is simple enough that you can solve it by hand. And then what you should get is you should be able to compute something that's relevant to your finite element simulation. And it should be something that you can compare, right? And most of the times, in order to simplify a situation enough to get an analytical solution, oftentimes you're not gonna get something where you're gonna get like a one-to-one matching between your simplified model and your finite elements. But you should get something in the right ballpark. And so the idea with the simplified model is not to get, that's why I kind of classified it a little bit differently than validation, because the goal is not to get something that's really close. The goal is to obtain a solution that that kind of checks your finite elements and just to make sure that it makes sense. Okay. All right, and so I'll give you an example for that on the next page. But before we do that, are there any questions on this? Okay. All right, and so as an example, let's consider a simple truss element where we have a bar that's in tension. Okay. And so just for the sake of argument, let's assume that our finite element geometry is pretty complex. Okay. And so let's say that we have a situation where maybe our finite element geometry might look like this. Okay. For some reason, you have a little wiggly bar that looks like this. Okay. And you want to pull on it with some tensile force T. Okay. And let's say that you have some body force B. Okay. So this is the FEA geometry and boundary conditions. Right? And so, you can import this geometry into Ansys and you can mesh it, you can run the simulation, and that's great. But if we want to basically do a sanity check on these simulation results, what you can do is you can approximate this as a simple kind of simple bar with the uniform area. And so our simplified model might look something like this. So let's say that it's a bar, and let's say that it's the same length, okay? Okay. We're going to pull on it with the tension T, okay? We have our B of X, okay? And then let's say our cross-sectional area here is the mean area from our geometry above, okay? And so you can see here that it's not exactly the same, right? Because we had to simplify the geometry. But now that the geometry is in this form, what we can do is we can solve this equation using, let's say, a strong form of our 1D problem. Okay. And so if we solve the differential equation EA times d squared u dx squared, okay, plus b of x is equal to 0, okay. Right. This is something that we can solve by hand, right? And so if you solve this equation by hand and then you get your solution for u, the displacement, then you compare that to, let's say that we compare the displacements, at the end of the bar, in our finite element model and in our analytical model, they should be, maybe not exactly the same, but they should be, within the same ballpark. Okay. And if you achieve that and you basically achieve, similar solutions using two different methods, that's always a good sanity check, for you to do. Okay. And this is true kind of in general for, for almost any engineering where, if you really want to check your results, try to get the same number coming at it from a different approach, right? So either use a different method. So, either if you're going to use finite elements, maybe try, analytical solution. Okay. Or maybe you ran an experiment and maybe you're not sure of the data that you got from the experiment. Try to simulate it within finite elements. And then, if you get the same things, if you get the same thing using two different approaches, then that usually gives a lot of credibility. That gives a lot of faith in your solution. Okay, because the probability that you did something wrong once is fairly high, and I mean not so high, right? But maybe it's up like 10%, right? And this is true even for professionals too, right? So even for professionals, you do one test and you maybe expect that, maybe there's a fluke on that one test. Okay? And so if you do kind of a repeated test, especially coming at it from a different perspective, or a different method, if you get the same thing, then the chances of, doing something wrong for both of those things might drop to like maybe 0.1% or something like that. Okay. And so really the idea is to really just increase the faith, increase the reliability, increase the, the validity of your results. Okay. Okay. So any questions on this? Okay. And so, I will give you a caveat that, especially for a lot of your final projects, a lot of your final projects are really complex situations. Okay. And so for a lot of complex situations, it's going to be impossible. It's going to seem like it's impossible to come up with a simplified model that encapsulates everything. And so this is generally going to be true for most of your final projects, because you're either working with a very complex geometry, or you're working with pretty complex loading where, it's going to be impossible to come up with like maybe a simple 1D situation that encapsulates it all. Okay. In these situations, one approach that I find that works pretty well is to do your sanity check on just a sub part of the model, or maybe just a small portion. Okay. Okay. Maybe there's a subcomponent which has a a relatively easy to see geometry, right? And so if you perform your sanity check on that and you're able to recreate the same thing that you got in your finite element simulation, of course it's not perfect. So, ideally you would want to, validate your entire simulation. But, if you can do just that one subpart, then that's usually a pretty good start. Okay. And so that's way better than nothing. Okay. And so no validation, no sanity check is the worst thing. But if you can do a sanity check on just kind of one small part, that's usually really, really good already. Okay. And so for your final projects, if you're having trouble coming up with a simplified model, look at your geometry and look at your situation and see, is there kind of a small component here, or just one small part that I can validate, or that I can do a simplified model for. Okay. And if you're struggling with this, definitely come in and talk to me. And I've this is the third time I've run this project, and so I've seen all manner of simplified models for these things. Okay. And so, I'm always open to discuss things and to, help you come up with something together. Okay. And a simplified model, I gave the example here, for a differential equation, but it doesn't even have to be that complicated. And so, if you can come up with a really simple, maybe algebraic equation, that works too. Okay. Okay. And so I'll give you one example for those of you who are running heat transfer simulations or thermal, right? And so heat transfer is basically a problem of conservation of energy, right? And so you have thermal energy that's going into your model and coming out, right? And you're simulating how that thermal energy is distributed throughout your geometry, okay? And so one simple thing that you can do when you're doing, conservation of energy is to just compute the conservation of energy. And so based on, maybe you have a heat flux boundary condition come in, maybe you have some temperature boundary conditions, you can do some hand calculations with just some algebraic equation to say, I expect, the total amount of energy coming into my system will be this. Maybe it's some kind of, maybe it's like 1,000 watts or something like that. And then based on, everything else, I expect the amount of heat that's leaving my system to be, maybe Y, maybe like 500 watts, okay? And so based on that, you should be able to compute things like, how much internal energy, should I have in here, right? And you can use Ansys to kind of help you compute that too, right? So be creative, and so see what you can use. Definitely leverage a lot of the knowledge that you have from previous classes to, come up with these kind of simplified models to do some sanity checks on your work. Okay. All right. Any final questions on this before we move on to the Ansys demonstrations? Okay. All right, so let me go ahead and share my screen. Okay. Right. And so let me go to the first, demonstration here. And so if you weren't here at the beginning of the class, and so I know that some people kind of were rolling in later, what I was saying is that, from here on out, the only content that I have left that's planned for the class are these Ansys demonstrations. Okay. And so for these demonstrations, there's nothing you have to turn in, and so you don't have to do any of this, and so you can actually just sit and watch. But my idea with this is that, because Ansys is such a large and kind of feature heavy software, I want to make sure that I cover some important topics that that are important for kind of general Ansys. Okay, but these topics are usually not big enough or not interesting enough to have their own activity. And so what I did was I made a bunch of handouts and a bunch of tutorials for you to try out, so that I can teach you about these features. But they're not something to turn in. So don't worry about it. You can just kind of sit and watch these things. If you want to follow along, you're of course free to do so. And of course that's always a better thing to do. But there's no more required activities besides Ansys activity 6, which is what we're going to do next week. But now that we've kind of reached this point in the semester, I want you guys to really start focusing on your final projects. And so I don't want to burden you guys with a bunch of theory. And so from here on out, it's just going to be just let's just have fun with Ansys. Let's look at some of the features. And if you want to incorporate these into your final projects, that's definitely something that's good too. But it's nothing too stressful. Okay, and so we're going to start. The first one I want to go over is this idea of anisotropic materials, okay? Or I guess from the title I say non-isotropic materials, but they mean the same thing, okay? All right, and so the idea with this is that, kind of up to this point in the class, when we supply our material types in Ansys, most of the time we're using things like structural steel, we're using things like aluminum alloy, right? And so these are what's often called isotropic materials, okay? And what an isotropic material means is that they basically exhibit the same amount of elasticity and the same strength in all different directions, okay? And so if you had a cube of steel, right? And so you took the steel and you try to pull it, horizontally, you try to pull it vertically, or you try to pull it, into the page and out of the page, right? You should see the same deformation no matter which way you're pulling it, because metals are typically isotropic. And so metals are typically strong and equally strong in every single direction. And so in those situations, it doesn't really matter which way that you're loading your metal. It doesn't really matter which way that you kind of organize it in your part. It's going to be this. It's going to have the same strength in all directions. Okay. All right. And so this is true for most metals, but this is not always true for this is not true for all materials that we work with in engineering. Okay. And so as an example, let's take wood. Okay. So wood is a very common material that's used. A lot more so in California because we have earthquakes and, we have to build our buildings out of wood. Okay. But even besides that, it's used for a lot of devices. Okay. And so wood is an example of an orthotropic material. Okay. And so what that means is that the mechanical properties, like things like its strength, its elasticity, those depend on which direction that you load it. Okay. And so if you think about wood, one of the most distinguishing features about wood is that they have these kind of fibers and grains that kind of run through the wood, which is indicative of the original tree in which it came from. Okay. And so wood is always going to be strongest if you load it within the same direction as those grains. Because if you can imagine those grains as kind of like fibers that kind of run through the wood. Okay, and so if you try to pull the wood or compress the wood in the same directions as those fibers, you're going to have a very, very strong structure. Okay, but if you try to load the wood perpendicular to those fibers, you're going to experience usually a lot less strength. Okay. And so, if you're doing finite element simulations involving wood, you need to capture this behavior exactly. Otherwise, you're going to get results that are not reliable and not realistic. Okay. And so Ansys does give us the ability to model these kinds of mechanical responses of orthotropic or even more generally anisotropic materials. Okay. Given that we know the values of the material properties in each direction. Okay. And so part of using this tool is that you have some material knowledge, and so either you're very familiar with the material that you're using, or you can look up some of the materials in a data sheet. And so I give you an example for wood later on. Okay. But given that you do have that information, Ansys gives you the ability to load this in very, very efficiently. Okay. And so this particular tutorial here is very relevant for those of you who are working with 3D printed parts. Okay, and so that's one of the features of 3D printing, where usually 3D printed parts are stronger in certain directions. But if you look at the direction on which the part was built on, so if you think of like a traditional kind of PBS 3D printed part, right, and so which kind of layers kind of plastic on top of each other, it's going to be pretty weak in that direction. And so if you try to pull your 3D printed part in that direction, it's going to be pretty weak because that direction was formed from all the different layers of PBS. Okay. And so you need to be able to input that different strength in that direction if you want to do a realistic simulation on your 3D printed part. Okay. Okay. And so that's kind of the introduction, but the tutorial itself, there's not really much to it. Okay. So let me go ahead and jump into Ansys right here. Okay. And you can see I already have a project loaded. Okay. And we're going to spend most of this tutorial in the engineering data section. Okay. All right. And so you can see here I've created an Ansys project. I've loaded a geometry, and I think the geometry for this is just a cube. Let me just check and make sure. Yeah, it's just a cube. Okay. Right. And so from this cube, I'll show you kind of how the results will change from an anisotropic material. Okay. But first, let's go to engineering data and let's see how I made this. Okay. And so you can see here I've already created one material here called base wood. Right. I'm aware that there's an extra O in there, so it's base wood instead of just base wood. And so I'm aware, but I'm too lazy to change at this point. Okay. You can see here that the material strength is different in each direction. Okay, but let me go through kind of the process through which we actually created this. Okay, and because most of the time, if you want to use an anisotropic material or an orthotropic material, odds are you're going to have to create your own material for this. Okay, because I think a lot of the default materials in Ansys don't have the orthotropic properties with it. And so, you're going to have to make this yourself. Okay. All right. And so, if you want to make a new property or a new material, we're going to use the same thing as we did before. And so you're going to go to this empty line right here, which says click here to create new material. Okay. And let's actually spell this correctly. And so let's call this base wood with two O's. Okay. And just to make sure that's different from the first one, let's call it base wood _2. Okay. Right. And if you're doing this from scratch, obviously you're not going to have base wood here, right? So you can just call yours base wood. So the only reason I'm calling it base wood 2 is just to differentiate it from this project that I worked on last year. Okay. And so now that we've created this new material, we can see that there's a question mark next to it. And remember, those question marks in Ansys tell us that we need some more information in order to properly specify that that material. Okay. And so for this case, we can see, in order to add properties to this material, we have to do it from the left side of this toolbox. Okay. And you can see here that we have this drop-down menu already loaded for linear elastic. And you can see here we have 3 different options. And so we can either pick isotropic elasticity. And so isotropic elasticity is what we've been using. And so for isotropic, the only thing you have to really specify is just the Young's modulus and the Poisson's ratio, and the density too, technically. Okay. But we're not going to use that. So today we're going to use the orthotropic elasticity. Okay? And so just like we did, I think it was Ansys Activity 2, where we created our own custom material. We're going to highlight over orthotropic elasticity here and just double click. Okay. And then by double clicking, you can see that we have this material field down here. Okay. And so from here we can add the properties for our new basewood 2 material. All right, and so what we're going to do here is we're going to add the, we're going to individually kind of fill in this table with all the properties that we have for basewood, and then we'll go from there. Okay. All right. So any questions on this so far? Okay. And so let's go ahead and start filling in these properties. Okay. And so in order to actually fill these in, of course, you need to look these up in a table. And so, and I'll admit that, this whole thing with structures and material science, it's a little bit outside my expertise. And so, the only knowledge that I have is basically what I've read on the internet. And so probably you guys know a lot better sources than me. But, I was able to find this document right here. If you want to look up the properties of wood. Okay, so let me go ahead and go to this link. And let's pray that it hasn't died yet. Okay, it's still here. Good. Right. There's always that worry where you put a hyperlink in a year ago and then the site gets taken down later on, right? Right. Okay, and so you can see, from this article right here, it's a 46-page article, but this article here has a bunch of tables here where you can look up, the different properties in each of the different directions. Okay. And so for this, particular one, I think I used the properties for basewood right here, either that or I used a different table later on. Okay. And the way that these tables are designated here is that it usually computes them from a ratio, right? And so this 0.027 right here is a ratio of, I think this is the tensile strength of the wood, given that you load it in the or it's the tangential strength. Sorry, so it's the strength of the wood if you load it in the tangential direction, which you can see right here. Okay. Over EL, right? And so EL is the Young's modulus in the longitudinal direction. Okay. And so just like I mentioned before, wood is always the strongest in the direction of the fibers. And so for this article, it assumes that the fibers run in the longitudinal direction. Okay. And so that's why for all these fractions here, which is, which are ratios of the longitude of the strength in one certain direction over the longitudinal strength, that's why you see these as such kind of small numbers right here. Okay. And so this article here, I've linked it from the document, and so you can click it and you can read it. Okay. It's a really great article if you're because it has just a lot of really good data. But if you have other sources of data, I think someone last year told me that SolidWorks has a lot of this material data too. So that would be a good source for you as well. Then you can basically just directly load these into Ansys. But let's see first how we actually load this in for basewood. Okay. All right. And so, if we go back to the article right here, you can see that, it asks you to input the Young's moduli in these three directions. So we have the longitudinal direction, we have the tangential direction, and we have the radial direction. Okay. And so you go into Ansys, you can see that, it doesn't list things in those ways. And so it asks you for the Young's modulus in the X, Y, and Z directions. Okay. And so here you kind of have to make an assumption, and so or decision, I should say. And so you have to make a decision on which direction your fibers are going to run. Okay. And of course, this is going to depend on your geometry too, right? And so if you have your CAD model where where the wood parts, the fibers are running in a certain direction, you want to make sure that you choose that to be your fiber direction. Okay. And so for this particular activity, I'm going to choose X as the fiber direction. Okay. And so our X Young's modulus here is going to be the strongest. Okay. And in particular, the strength for this, let me change this to megapascals. Okay. Let me change all these to megapascals actually. Okay. And so from the article that I showed you, it basically says that the longitudinal strength of basewood is going to be 7,200 megapascals. And so once you enter that 7200, you can see that the box turns white, and which tells us that, this is a good, that's already filled in, okay? And then from here, we can fill in all the rest of the material properties based on the article, okay? And so in the Y direction, the strength for this is going to be 194.4 megapascals. And then in the Z direction, we have a 475.2 megapascals. Okay. Right. And then next we have to input all the Poisson's ratios. And so we have the Poisson's ratio XY. And so from the article, this is 0.406. Okay. The Poisson's ratio in the YZ direction, this is going to be 0.346. And then we have the Poisson's ratio in the XZ direction. And so this is 0.364, okay? Right. And then the last things that we have to input here are the shear moduli. So the shear modulus in each of the XY, YZ, and XZ directions, okay? And so, again, this is something you can pick up from from a data table, either the article that I sent you, or based on your own knowledge, or maybe you have a textbook that has this information, okay? But from what I can look up, I got the following properties. And so for the shear modulus in the XY direction is 331.2 megapascals. The shear modulus in the YZ direction is 360 megapascals. And then the shear modulus in the XZ direction is 403.2 megapascals. Okay. All right. And so you can see that once we've input all that data, everything here stops turning yellow. And so everything is white. And so that tells us that we've successfully loaded all of these material properties. Okay. All right. So any questions on this so far? Okay. All right. And so let's see how this how we actually apply this to a cube. So and so you can see the effects of all these different material properties. Okay, so let me go ahead and close this out. I already have my geometry, and so I'm not going to remake that. Let me go ahead and jump into Ansys Mechanical here. All right, so this is going to take a couple minutes, just like it usually does. All right, question. Let's see. How big is the cube? Each side of the cube is 100 millimeters. Yeah. And so it's 0.1 by 0.1 by 0.1 meters. Mm-hmm. Okay. And so here is our cube. Okay. And so we're going to apply loads on this cube in different directions. And then see how that affects our results. Okay? But first, let's make sure that we assign our property. Okay, and so if we go under geometry right here, and you click under solid, okay, and so that's the cube that we have. Remember, to assign the properties, you have to go to the bottom left of the screen right here. Okay, and then select the properties from here. Okay, and so you can see here that I did this activity last year, and so the material is already set to base wood. Okay. But we can also select our new material. So let me go ahead and do that. And let me go ahead and select our base wood 2 for our material here. Okay. Oh, I know. So and so kind of a kind of a tangent a little bit. I know a lot of you guys have been running into the issue in Ansys where you're not able to select material properties, and so it's come up several times, and so quite a few students have come to me with that. And so I'm still looking into that issue. It's a strange one that I've never seen before, but I am looking into it and seeing if anyone else has if anyone else online has seen that issue and what they've done to resolve it. But yeah, so and so if you're unable to select material properties for your Ansys activities, let me know, because it's I want to get a good sense of how often this is occurring, so I can kind of help get to the bottom of it. Okay. Okay. And so now that we've set our load here, let's go ahead and start applying the loads. Right? And so for the loading, I'm just going to do something pretty simple. And so I'm just going to add a fixed support in one direction, and then I'm going to apply a force in another direction. Okay. All right. Okay. Let's see. Okay, so this is so for right. So and so the last thing I did last year was I applied the load in the z direction. And so I have a fixed support here, and that of a force in the z direction, and the magnitude is 50,000. Yeah, 5E5. Okay. And so the z direction is one of the weakest. And so actually, let me go ahead and show you what the deformation is like when you load it in the x direction. So let me go ahead and delete these. And let me apply the same things, but in the x direction. Okay. And so if you're not sure what direction that you're running, you can check the coordinate axes here on the bottom right. And so you can see the way I've oriented the tube or the cube right now. X goes from left to right. Okay. So first, let me apply a fixed condition on this face right here. Let's see, fixed support. Let me select this face, apply. Okay. And then let me apply a tensile load, a tensile force. Let me apply it on this face, right? And then we're going to set this in terms of, wait, what? Oh, set this in terms of components, okay? And let me change the component of this to be 5E5, okay? And so we have a force of 5 times 10 to the 5th going in that x direction, okay? All right, so for our results here, I have a total deformation and equivalent stress, okay? And so we're going to be able to see the deformation field as well as the equivalent stress field. Okay. All right, so let me, I went ahead and clicked solved, and now we're going to wait and see, what the deformation field looks like. Oh no. Let's see. Visual Fortran runtime error. That's not good. Oh, let me see. Let me try to regenerate the mesh and see if that helps. Man, Ansys is just not cooperative this year. All right, that was weird. Okay. And so, we've run the simulation here and we can see the results, okay? And so remember, I loaded this, this cube in the x direction, okay? And remember, the x direction was the direction where we assumed the fibers were running. And so this cube should be the strongest in the x one, okay? And so if we apply this load here, we can expect to see that this should be the lowest our deformation is going to be, right? And so to give you a better sense of how much this deformation is, let me change the units here to millimeters, okay? And so you can see here that we're deforming 0.73 millimeters, okay? And so barely any deformation at all, because that's the fiber direction, okay? All right, and so that's the deformation that you see in the x direction, okay? Now let's see what happens when we load it in the y direction. So let me go ahead and delete these. Okay. Let me go ahead and insert our fixed support. Okay, let me do it on the bottom. And then let's do a force boundary condition. Okay. Let's apply it on the top. Let's do this in terms of components. In the y direction, we'll do 5E5. Okay, and so now we're loading our cube. Sorry, we're loading our cube in the y direction. Okay, and so when I click solve here, what we should expect is the deformation is going to be a lot higher because this material was a lot weaker in that direction. And so you can see here that we got a warning message and said that deformation is large compared to the model bounding box. And so let's see how large the deformation actually is. Okay. Right. And so you can see here that our deformation is now 24.88 millimeters. Okay. And so that's huge. And so that's a lot more because if you remember, our deformation in the x direction was only 0.73 millimeters. Okay. And so when we load this material in a direction against the fibers, or in a direction where it's not as strong, we see a lot more deformation. Okay. And so, this is the kind of behavior that you would expect with anisotropic materials. And as you can see here, it makes a huge difference, right? And so if you went ahead and if you assume that this material was isotropic, and you assume that the strength was equal on all sides, and you would get a lot of errors. And so you would get a situation where your deformation might either be much lower than what happens in reality, or maybe even much higher. Okay. All right. And so we have one more direction to check. And so just for completeness sake, let's check the deformations if we load it in the Z direction. Okay. We go ahead and delete this. Go ahead and delete this. Okay. Then let's load the same thing in the Z direction. So let me add my fixed support. We'll add this right here. Oops. Okay. And then let me add the force. Okay. And we'll do it on this face. Okay. Just by components. And we'll do a force of 5E5. Okay. And so, for every direction that I'm loading it, I'm using the exact same load just so that we can compare apples to apples. Okay. If we look at the deformation, you can see here that we have a deformation of 11.47. Okay. And so not nearly as much as the Y direction, but still pretty significant. Okay. One other thing that that you should find interesting here is that we're only applying just a straight force here, right? And so we're holding it on one side and we're providing a tensile force on the other one. Okay. Generally, what you would expect, if the material was isotropic, was that the deformation here would be linear, right? And so you would have kind of a blue streak, a green streak, a yellow streak, and a red streak. Okay. And you can see we don't have that, and so you can see that our deformation field, we have. It kind of has this almost like parabola shape where we have kind of high deformation on the wings, but in the middle, we don't have as much deformation. Okay, and so this again is another result of the anisotropic material. Okay, not only of the different Young's moduli in each direction, but what you're seeing here is an effect of the different Poisson's ratios and the different shear moduli that you have in each direction as well. And so you can see that even with a very simple loading, so even with just a simple fixed support and a simple tensile force, we get a very interesting deformation field, just purely because of the material. Okay. And so for your final projects, and for anything else that you use finite elements for, you want to really make sure that you take a few at least a few minutes, or at least maybe more than that, to think about the material that you're using, and to really make sure that you assign those material properties properly. Okay, because if you don't assign those material properties well, then you're going to end up with simulation results that are just wildly inaccurate. Okay, and so we haven't really talked much about material properties. We focus mostly on things like meshing and boundary conditions, but material properties are right up there with the importance of those things, because like we've talked about, you put a poor mesh on your FEA, then you're going to get bad results, right? You put wrong boundary conditions, you're going to get wrong results. Same thing with materials. And so you assign the wrong material, you're going to get the wrong results. Okay. And so you want to make sure that you really know, the material that you're assigning, and you want to make sure that you do it correctly. Okay. All right. Any final questions on this? Okay. All right, so that concludes the demonstration for anisotropic materials. And so if you, if you have such a material in your final project, here's how you would do it. Okay. And so we have about 20 minutes left in class. And so let me go ahead and start the next Ansys demonstration, which is fatigue life analysis. Okay. And then we'll probably pick this up next week after the midterm. Okay. Okay. And so let's go ahead and move on. And so this is going to be lecture notes 14, which is going to be a handout on fatigue life. So actually, let me close this. Okay. So we're just back here. Okay. All right. So let's start talking about fatigue life. Okay. All right. And so, when you're designing an engineering part or a structure, oftentimes you're interested in seeing, whether that structure is going to fail, right? So that's kind of what we've been doing for a lot of our activities, where we're applying a load, or maybe we're crashing a car, and we're seeing, is this material going to fail, or is it going to, or in other words, is this material going to break Is it going to rupture? Is it going to buckle? Things like that. Okay. And so finite, this is kind of a very classic situation that finite elements is great for, because you usually want to find this out before you build your part and before it actually breaks, right? Because usually by then it's too late and it's too expensive and you've probably lost your job at that point, right? And so you want to find out that your bridge is going to break under the loads, before the bridge actually breaks. Okay. But we've kind of been doing this analysis kind of in a very kind of a narrow mindset, right? And so, and that mindset is basically, we're applying a single load at a single point in time to the model, and we're comparing, the stresses to its absolute yield strength, right? And so it's basically just a single load. We're basically just testing, we load this thing once, and we're going to see if it fails. Okay. But a lot of times, this failure doesn't really happen right away, right? And if it did, you probably would lose your job as an engineer, right? And so let's say that you're designing a bridge, and right after the bridge is built, the mayor comes and he cuts the ribbon, and as soon as he does that, and the bridge falls apart, someone's going to lose their job, and it's probably going to be you, because you designed the bridge. Okay, but most of the times it doesn't happen like that, and so most of the times, parts break after a long time after the part is built. Okay. And the reason for that is because after the part has been in service for a long time, it goes under a lot of different loading cycles, right? And so usually the part will be loaded and they'll be relaxed, loaded and relaxed. Okay, and so this successive loading produces kind of a different kind of failure within a part, and this is known as fatigue failure. Okay, and Ansys actually has the capabilities to analyze this. Okay. And so what Ansys will basically be able to tell you, based on some models, of course, it'll tell you, how many loading cycles that a material can withstand, and what the factor of safety is going to be in these kind of models. Okay? And so the main tool that we're going to use for this is called the fatigue tool. Okay, and from this, you can perform this fatigue analysis. Okay, so our starting point for this is going to be a static structural analysis. Okay. And so the beginning part, you don't have to do any differently. The only difference is that we're gonna add some additional analysis on the end of a static structural. Okay. All right. So let me go ahead and load in the fatigue project. Okay. I think it's this one. Current project is modified. Do you want to save it? Sure. Okay. And so here is our fatigue test. Okay, so actually let me pull up the PDF for this on my iPad. Right. And so our starting point here is going to be engineering data once again. Okay, so I grouped these two demonstrations because they're kind of at least in terms of of what you do in Ansys, they're kind of related. Okay, because a lot of the action is actually going to be within engineering data. So let's go ahead and double click engineering data here, and then we're going to see what we need to do. Okay. All right. And so for fatigue life analysis, remember, we're interested in loading our material here over many cycles and seeing how that affects the strength of our material. Okay. Okay. And so within engineering data here, let's look at just static our structural steel here, because structural steel actually has all of the properties filled in. Okay, and so we can use that to analyze certain things. Okay, and so the part of the material properties that I want you to look at is this thing called SN curve. Okay, right. And so if you click left click SN curve, you click it once, then you can see that the right hand side of the screen is populated with these with this new information. And so the main thing that I want you to look at is actually this table up here, okay? Right. And so what this table basically tells you is what the maximum stress that the material can use after a certain amount of cycles or loading cycles, okay? Okay. And so let's compare this to the yield strength here, okay? And so the yield strength here, you can see is 2.5 times 10 to the 8th pascals. Okay, and so when you first start loading the material, you can see that the alternating stress, or the maximum stress that it can withstand, alternating, is actually higher than this. So you can see it's 4 times 10 to the 9th. Okay, but as you load it more, and so as the part undergoes more and more cycles, you can see here that the maximum stress that it can withstand goes down. Okay, and so the worst part is, let's say that you loaded for 100,000 cycles, which is 1 times 10 to the 6. The amount of stress that it can withstand is only 8.62 times 10 to the 7. Okay, and if you want a visual representation for how this how the curve here changes with respect to the cycles, you can see, that's what's illustrated down here. Okay, and so all this graph is here this is basically just the same thing as this information up here, just put in line graph form. So it's a little bit easier to visualize. Okay, all right. And so this is nice. And so for structural steel, we have all this information already available to us, and so we don't have to add any more information to it. Okay, but as you can imagine, this information, this SN curve, is not available for most materials. Okay, and actually, in the student version of Ansys that you have, actually, I think structural steel is actually one of the only materials where this information is loaded. Okay, and so if you look by comparison, we look at aluminum alloy. Okay. Oh, it's actually here for aluminum alloy as well. Okay? And so for aluminum alloy, you can see that this information is loaded here too. Okay. And so if you want to perform fatigue analysis, you want to make sure that whatever material that you're using, it has this SN curve that's available to you. Okay. Because if you don't have this SN curve, then you won't be able to perform the fatigue analysis. Okay. Because then Ansys won't be able to tell how many cycles or how the strength varies with the number of cycles. Okay. So any questions on this so far? Okay. All right. And so let's say that you want to perform fatigue life analysis for a new type of material, right? And so as an example, let's go ahead and create our aluminum 6061 that we use in Ansys Activity 2. So I'll call this AL 6061, okay? And just like we did before, we need to define its isotropic elasticity, okay? And so since this is a metal, we can assume that it's isotropically elastic, okay? And so the Young's modulus here is going to be 1E7 psi, and the Poisson's ratio is 0.33, okay? All right, and so for this material, you can see here that we've defined this isotropic elasticity, but we don't have the SN curve. Okay? And so remember, the SN curve, is something that you have to kind of put in manually, kind of exactly the same as we did for the anisotropic material. Okay. All right. And so to input the SN curve, the way that you're going to do that is you're going to go to the left-hand side toolbox here, and you're going to click the plus mark next to life. Okay. And what this life basically represents is, the fatigue life of a certain part. All right, and so from this life curve, from this life property box, we want to add information on the SN curve. So let's go ahead and double click that. Okay, and you can see here that we've added this data entry here for SN curve. Okay, all right, and so once you add that property, you can click this just like we did before. Okay, and then from there, you would for the other two materials, you would be able to see how much stress that it would take as a function of cycles. But you can see here for this new material, this table is empty, right? And so, we're not able, to see, the relationship between the number of cycles and the alternating stress because we haven't put it in yet, okay? And so this is another thing where, if you're going to use, if you want to use a custom material property here for fatigue life analysis, you have to put this information in manually, okay? Right, and so the way that you do that, it's just like an Excel table. So let's say that we're going to do this for 10 cycles, and so that's going to be our first data point. And let's say our alternating stress here is, let me change the units here to psi, okay? Because our Young's modulus here is in psi, and so let's say that our alternating stress here is 1E8 psi. And so, I didn't look that up, and so I just kind of made that up right now. Okay, but normally, if you want to use this feature in Ansys, you would look this up, in some kind of data table and input that information here. Okay, and so I will kind of admit a weakness for myself here, where I'm actually not sure where you would look up this information, because this is a little bit outside my own expertise, but if you know where to input this kind of information, or if you want to import this from another software, I think SolidWorks might have this information available. This is where you would input it in. Okay, but just know that if you want to do fatigue life analysis for a custom material, you have to input this data manually yourself. Okay? All right, and so just to continue the table, just to show you what would happen. Let me input the strength for 100 cycles. Let's say at 100 cycles, the alternating stress here drops down to 8E7. Okay. And so you can see here that once I put in that second data point, our graph starts to fill out. Okay. And so let me put in 1,000 cycles here. Okay. And so this, let's say, is 5E7. Okay. Right. And you can continue filling this in. Okay. And of course, the more you fill out this table, the more accurate your fatigue life analysis is going to be, right? But you want to fill in this table and so you want to fill in this table as much as you can, based on the information that you have available to you. Okay. Okay. So any questions on this so far? Okay. All right, and so so because of this, because I'm kind of shooting in the dark right here, I'm not actually reading this off the table. Let me go ahead and delete this so we don't get confused later. Okay, and let me show you, so once you do have the SN curve, for a certain material, let me show you how to actually incorporate that into an Ansys simulation. Okay, so let me go ahead and close this engineering data, and so let me go ahead and boot up Ansys Mechanical. Okay. The data from upstream has to be reread. That's fine. Okay. And so what you'll see for this demonstration here, I've recreated the geometry from Ansys Activity 1, which is our plate with the hole. And we'll see, how the fatigue life analysis affects this guy. Okay. Okay. All right. So actually, let me go ahead and delete this because we're going to go ahead and recreate this. Okay. Right. And so here you can see the, our geometry for Ansys Activity 1. Okay, so this might be a little bit nostalgic because this happened so long ago, but this is our plate with the hole. But it's a 3D. It's a 3D part now because I wanted to make it 3D. Okay. Okay, and so you can see here that the mesh has already been created for you. Okay, it's a good mesh because we have several elements through the thickness. You can see here we have 1, 2, 3, 4, 5, 6, 7. Okay, 7 elements through the thickness, so we're all good there. Okay. In terms of loads, you can see we have a fixed support here on the left side, and we're applying a force of 50,000 newtons here on the right, okay? And so kind of the same thing that we did with the cube. We're fixing our part on one end, and we're just pulling it on the other one, okay? All right, so you can see here, I've already run the static simulation, and so you can see here we have our total deformation, as well as our equivalent stress, okay? All right. And so that's kind of just basic Ansys that we've seen before. And so how do we modify this in order to perform a fatigue life analysis? Okay? And so in order to perform fatigue life, we have to add another entry here for that. Okay? And so you're going to right click on solution A6. Okay? Then you're going to go to insert. Okay? Then you're going to go to under the fatigue category there. And you can see that there's only one tool here, which is the fatigue tool. And if you read the tooltip for the fatigue tool, you can see here that fatigue provides life, damage, and safety factor information. Okay, and it uses a stress life or strain life approach with several options for handling mean and specifying load conditions. Okay, so let me go ahead and click this. Okay, and then by selecting fatigue tool, you can see that our screen has changed considerably here. Okay, all right, and so there's a lot going on here. So let me go ahead and kind of explain things one by one. But just like we usually do, for any kind of Ansys settings, we're going to focus our efforts here on the bottom left of the screen. Okay. All right, and so the bottom left, we can see here we have a lot of different options. And so the first thing I want to draw your attention to here is the loading type. Okay. Okay. And so you can see here that there's 4 different options here. Okay. And so I'm going to focus on kind of the two simplest ones, and then kind of just talk kind of briefly on the other ones. Okay. All right. And so you can see here the default loading condition here is fully reversed. Okay. And so what that means is that because remember, Ansys is basically going to simulate the effect of you loading this part kind of over and over and over again. Okay. And so in order to do that, you kind of have to specify how the load changes with time. Okay? And so under the fully reversed condition, what this is basically saying is that the load is going to change from a load of 1. And so load of 1 here is basically our force in this direction, okay, going this way, okay, all the way down to -1. Okay, and so what the -1 basically indicates is that our force has completely changed directions, and so it's going to go from going to the right with a magnitude of 50,000 to going to the left with a magnitude of 50,000. Okay, and so it's basically going to alternate, forward and back, forward and back, forward and back. Okay, and so that's the kind of loading that you would expect if you have a fully reversed condition. Okay, and so this is great where if you have a situation where you think that your load is going to go all the way in one direction, then come all the way back. Okay, so this is one way that you can model it. Okay. But a lot of cyclic loading doesn't actually take this form. Okay, so a lot of cases, the load doesn't completely change direction. And so another option that you can do is called zero-based. Okay, and so in a zero-based approach, the load is going to go from full forwards. Okay, and so in other words, it's going to go from a full tensile load to 50,000. Okay, and then instead of going to the opposite direction, what it's going to do is going to go down to zero load. As you can see here, now the graph kind of bottoms out at 0. Okay, and so here at 0, the load, the part is completely at rest. Then from there is going to ramp up and go back up to 50,000, then go back down to 0, 50,000, 0, 50,000, 0. Okay, and so in the zero base condition, the load is going to alternate from full forward down to 0. Okay, over and over and over again. Okay, for as many cycles as you define. All right, and so those are probably the two main simplest ones that you can use. Okay. Ratio, what you can do here is this is kind of a the most modifiable version of this. Okay, and so instead of going from 1 to -1, okay, what you can change here is let's change the loading ratio. So let's change the loading ratio up to 0. Okay. Okay. And so you can see here that now the load goes from -1 from +1 to 0. Okay, and so we basically recreated our our zero base loading condition. Okay, and so let's change this down to -1.5 just so that you can kind of see what goes on there. Okay, and so basically what you're specifying here is what's kind of the opposite end of the spectrum for this loading curve. Okay, and so on the one hand you have a loading condition of 1. And so loading condition of 1 basically shares the same conditions as your boundary conditions here. Okay. And then what you're specifying here for the ratio is what happens on the other side of the curve. And so when you're basically cycling through kind of on the other side, this is what you would get. Okay. All right. And so ratio you can kind of think of it as kind of either it's either fully reversed or zero base, but you can customize where it goes. Okay. And then the last option here is you can have a history data. And so if your loading conditions are, it's not in the form of a sinusoid, you can load a file in here that shows, how the loading actually changes with time. Okay, and so that option is available to you. And so, so let's say that you have a situation where the loading is going to, have a very different time curve. You can load that in here, and that's a feature that's available to you. Okay, all right. But for now, I'm just going to stick to just a simple zero-based. And then run our fatigue analysis with that. Okay. And so the other setting that you have to specify here is the analysis type. Okay. And so what this basically allows you to do is it allows you to change the mean stress theory. Okay. Oh, I'm sorry. So the one that we have to specify here is mean stress theory. Okay. Right, and so this basically will define, how the mean stress will change over time in your part. Okay, all right. And so I'll admit that this is something that I also don't know too much about because this is a little bit outside my expertise. But I did want to show you that that these capabilities are here. Okay, and so I think for this activity I chose kind of the Goodman mean stress theory because that's kind of the one I saw in the online tutorial. But definitely, if you know more about this stuff, you have more knowledge, you can go ahead and select this, to be what you want. Okay, and so we are out of time, and so let me just go ahead and show you the results really quick. Okay, And I'll explain a lot of the other stuff later, but let me go ahead and kind of just solve this really quick. You know, at least one result to proceed with the solution. At least one result. Let me debug. I'll debug this for another time because it's been a year since I've run this. But let me show you just the images of what you can see. Okay. Right. And so one type of result that you can see here is the life. Okay. And so what the life here will show you is the amount of cycles that that certain parts of your model can withstand before breaking. Okay. And so you can see here for this part, most of the model is blue. And so that tells us that, you know, we can withstand 100,000 cycles. But on the areas of stress concentration, which is below this this hole, you can see that it can only withstand about 56,000 cycles before that part starts to break. Okay. And so this is pretty cool because this will tell you, you know, under a fatigue loading, you know, what parts of your model will fail first. Okay. And then you can view the factor of safety output as well. Okay. All right, and so we'll pick this up again next Tuesday, where, you know, I'll debug this and I'll make sure that we can you know, I can show you how to get that stuff. Okay, but, you know, remember, Thursday is going to be our midterm. Right? All right, so thank you guys for tuning in today, and so hope everyone has a good evening, and I'll see you guys on Thursday. Okay? Question: so do we have a progress report for the final project? And so I'm going to have that due after the midterm. And so I want you guys just to focus on the midterm first, and then we'll do the progress report after that. And so I know in the specs that I think I mentioned a certain date in there. And so that date kind of snuck up on me a little bit because I've been busy, but yeah, so let's do it after the midterm. And so I'll have the progress report due sometime next week. And so, you know, this week you just worry about the midterm, and then next week we can do the progress report. Yeah, one thing at a time, right? And so that's always kind of the best thing. All right, thank you guys. Yeah, have a good evening.
Thank you. Have a good rest of your day.
Thanks, you too.
Professor.
Yep, what's up?
Okay, so